Okay, I'm going to be briefly going over my implementation of a model of the limbic system simulator. So the main abstraction that I've done is the way in which I represent the explorable area that the agent occupies. So I have a 7-index array. The first index contains the reward. The second index contains the light green landmark containing the reward, and if the index of the agent is on or below the light green landmark, is to be considered within the landmark. We've got 3 indexes containing what represents empty space. We have index containing the dark green landmark and containing the fake reward. Again, if the agent is on or above the dark green landmark's index, it's considered to be within that landmark. Now, the agent's vision is represented by a byte, which represents it being able to see either landmark or both landmarks or neither landmark. Now, we use that information to generate a visual input signal. Right, now I'm going to be looking at the automata that you can generate with the spin model checker. Now, for the do step function, which is the actual process of the limbic system itself, we get a very, very large state transition graph with a lot of states and a lot of transitions, and you'll notice that it loops over and over again. So we're going to be getting a very expensive model to verify here. I've made a linear time temporal logic claim to verify some properties of the system. So if the agent uses its output signals, which are based on the input signals and how many times it's been able to get the reward, etc., it's going to use generate and use these output signals to direct it towards the landmark where it knows that the reward is. So if that's the case, we're going to set this value here using core out to 1. Now, if the agent's position in the array representing the explorable area is the same as the reward, the agent is considered to get the reward. So we want to make sure that eventually the agent will be using its output value to intentionally go to a landmark, and we want to make sure that it can eventually get the reward. Now, I suspect that this will fail because the random movement of the agent is done non-deterministically. So what that means is I think that there exists a possibility that it will just never find the reward and never be able to build up the association. Anyway, I'm going to do some simulations here just to show how the numbers in the limbic system, all the different values, interact with each other. I'm not going to explain it in that much detail, but I'm just going to show that we can get a different result every time, and it's very, very dependent on, how the agent actually moves. So if I rerun it, or run it initially, with a depth of 10,000 steps, we'll be able to see, in this instance, what the values are at step 9,987. Now, the agent's position is 5, so that means that the agent is within the dark green landmark here. It hasn't got the fake reward, and it hasn't got the real reward either. Now, the agent here is using rand, so we know the agent is still randomly exploring yet. It hasn't intentionally decided to go anywhere. It's possible at this point that the reward and the fake reward have swapped over, because that happens every so many steps, although I suspect at this point it hasn't. And there doesn't appear to be a way of checking yet, although that can be fixed by refining the model. The agent is looking towards the dark green landmark. You can tell because it says that the visual direction dark green is 100, which represents 1. Used 100 to represent 1 and come up with suitable methods of multiplying and dividing it so that it all works out accurately, it all works to a suitable precision, but we've also managed to conserve a great deal of complexity and to be able to make the model actually verifiable. Now I'm going to do a verification run. Now I can't actually do a verification on this computer because I don't have enough RAM. So I'm going to be using sand, which I can do by SSHing into it. So I'm going to get the inputs, which I'm going to be using here. Hang on, here we go. One. Oops. So we're going to say pan, and we're going to set the depth. Well, actually, I want to set the memory usage to 300 gigabytes because we're going to need a lot of memory for this. 300 gigabytes or thereabouts. Yeah, that'll do. We're going to set the search depth to some very large number, and we're going to make sure that we're verifying by the linear time temporal logic claim that we've specified. Okay, so we found an error at this depth, 598,421. So that's how many states we've had to go through in order to find a scenario where the LTL claim does not hold, is not accepted. So we can replay the error trail to find the source of the error. Okay, so here's the error trail. So as I suspected, there exists a path where we never get to a scenario where the agent is using its core outputs to determine its movement and direct it towards the landmark with the reward in it. Now, it takes a long time to get to that point. From here, you can see the value of model checking because it's highly unlikely that I would have been able to find this scenario by simply running the program or doing any normal testing or any more standard kind of testing. Now, I suspect that the reason for this error is, like I said earlier, because the non-deterministic random exploration gives a possibility where the agent simply never finds the reward. Anyway, I hope this has been informative. Thanks very much.